So, hello people, how are you doing? So, today I'm going to talk about the JohnsonCook plasticity and damage model. And I'm going to first start with some theory, and further, I'm going to explain a simple model in Abaqus because I think it's going to be good for the better understanding about the model. So, let's start with the Johnson TensorFlow equation. This equation models the plastic region in the analysis. As you can see here, the stresses are a function of the plastic strain, of course, the strain rate, and the temperature. If we just account for the plastic strain, we have three coefficients. We have the A, the B, and the N. The A, B, and N models the stresses in the plastic region just like a parallel equation. And everything is defined, is controlled by the equivalent plastic strain. So you just the plastic strain that happens after the yield point, as you can see here by these double arrows. Uh, we have also the influence of the strain rate that is controlled by the Chi coefficient. And the strain rate dependence is assuming to follow this ratio right here. So this ratio is the equivalent plastic strain rate divided by the reference strain rate, or the sigma dot PL and sigma dot 0. So why do you have to model this strain rate dependence? Because as we know, as is showing this scheme, if we grow the strain rate, or if we deform the body in less time, the stresses starts to get a little bit bigger. So of course it has a big influence in the plastic evolution. If we have a model that has high strain. The equivalent plastic strain rate is calculated in Abaqus by this equation. So what this equation says to us that if the strain rate in the model is equal to strain rate reference, this part of the equation goes to zero, and the equivalent plastic strain is just like equals to the reference strain rate. But as soon as the strain rate in the model is bigger than the strain rate reference, the equivalent plastic strain just grows exponentially. Of course, controlled by the C coefficient. Well, last, we have the temperature effects that are controlled by the M coefficient. And the temperature is calculated by this dimensionless parameter theta star. So the theta star is calculated by these three sets of equation. Let's first start with the definition of these variables. The theta transition is just the temperature where the yield stress, the yield stress starts to be affected by the temperature. It's kind of confusing, I know, but basically it says that if the temperature in the body is less than the theta transition, okay, we just says that it has no influence. The temperature has no influence in the plasticity. So it goes to zero and it goes to 1 here. So just this part of the equation does not affect the model. In other words, the theta transition basically is the room temperature for, of course, the most cases. Uh, we also have the theta melt, that is the melt temperature. No problems about that. So if the temperature in the body is bigger than theta melt, as we can see here, the theta star goes to 1. So when it goes to 1, it goes to 0 and everything vanishes. What it is saying that the body starts to have a behavior like a fluid. So no more stresses are generated when we have a strain shear, okay, a shear strain, sorry. And by last, of course, the theta is just the temperature in the analysis. Well, let's move on now to the Johnson-Cook damage model. Again, we have 5 coefficients, D1 until D5, that are material parameters that models the plastic strain at failure. So is the point. So is the strain where the body can hold anymore, and the element lost all the structural responsibility in the analysis. We have just defined some parameters here. First, let's define this eta. This eta is the dimensionless pressure stress ratio. Sorry for this E word right here. So it's just a relation between the hydrostatic tension, sigma m, and the von Mises's equivalent stresses, sigma vm. The hydrostatic stress is just the average of the normal stresses, and the von Mises stress is just the von Mises equation that we all know. We also have the R, that is the dimensionless plastic strain rate. That's just the ratio between the equivalent plastic strain rate and the reference strain rate. No question about it. And the theta star it has the same meaning that the theta has in the TensorFlow equation. So it's the same three set of equations. But let's move on for a deeper looking in this equation. If we take a look in the first part, in the first two pairs of two pairs of brackets in this damage model, we can see that when the eta coefficient increases, or in other words, when this ratio increases, the equivalent plastic at failure decreases. So if the body has this scenario with bigger hydrostatic stresses and lower von Mises stresses, the plastic strain can be developed, and the body fails like a fragile material, or tends to have this failure mode. We can check this result in this graph that was taken from the JohnsonCook paper, and we can see here that if we increase this pressure, this ratio, this eta right here, the equivalent plastic strain at fracture start to decrease. It's all evident here. Move on to the second part of the Johnson-Cook damage model equation. We can see that we have the strain rate influence in the equivalent plastic strain at failure. And what he is saying here that if the D4 is positive, which normally is, the strain rate at fracture increases with the strain rate. And the same thing says this part equation that deals with the temperature effects. If D5 is positive, the strain rate at fracture starts to increase when the temperature increases. So it's proportional to the temperature. These last two results are not that intuitive, but are confirmed by these results right here. The strain rate is not that apparent here, but we can see that if we increase the strain rate, the equivalent plastic strain at failure grows a little bit, just a little bit, but grows actually. Um, However, the temperature, if we increase the temperature, it really increases well. So you can see the temperature has a bigger effect on the strain, on the plastic strain at failure, but the both parameters are proportional to the both parameters affect the equivalent plastic strain in the same way. So I think I covered just in introduction about the JohnsonCook model, and I will suggest you guys if you want to learn more about it. We have the JohnsonCook original paper right here, and of course the Abaqus documentation. So thank you very much. In the next videos, I'm gonna talk about the how you implement this model in Abaqus, and I really wish you like the videos. So thank you.